So guys, good evening everyone. We are on live now. So I hope everyone can hear me. You guys can see me. Okay. So basically we are discussing about very important compounds. Okay. So that is a very important chapter. What we are going to call it as? We're going to call it as a periodic classification, right? Okay, there is a power cut guys here. So sometimes net may go, but don't need to worry about that. So whatever we have discussed in the previous class, we will discuss that one first. Okay. So now without wasting time, we'll start discussion about our chapter, right? So that is classification. And we know that how to remember these elements. That is Helena. How to discuss this one? Helena ka Ruby close friend. Helena ka Ruby what? Close friend. Okay, you can remember that one like that. So Helena ka Ruby close friend like that you can remember. The next one, beta, mange, car, scooter, bap, raji. So that is the another one trick I told you for the S block elements. For P block elements, Bal Ganesh, Ganesh in Thailand. So that is boron, aluminum, gallium, indium, and thallium. Next one, chemistry, Sir Geetam, having sneezing problem. So that is carbon, silicon, germanium, tin, and lead. Sn means stannous and Pb means plumbum. That is lead. Okay, so lead is simply called it as plumbate. So that's why we given as Pb. And tin is called as Sn, stannous. So that is why we given Sn. Next one is nitrogen. That is New Zealand, Pakistan, Australia, सब बिक गया है. Big gaya means what? In which? That is they have been sold out in IPL. So that's why nitrogen, Pakistan, arsenic, SB means antimony. SB means what? Antimony. Big gaya means what? Bismuth. Okay, so this is the trick we learned in the previous classes. Okay, so just a minute guys, we have some background noise. Yeah, now everyone is mute. Now next we can go to the next one, that is हो साइंस से तेरे को प्रॉब्लम है. So that is Ho means oxygen, science means sulfur, Se means cellurium, Te means tellurium, problem means polonium, PO means polonium, He. Okay, simply that is nothing but you can remember that. Next one, 17th, group 17th is what? Father, collector, brother, inspector, attention. So that is fluorine, chlorine, bromine, iodine, cadmium. Okay, that is attention. I hope you guys can remember the elements. Again, Helena ka Ruby close friend hai. Beta mange car, scooter, baap, Raji. Okay, I hope you guys can remember this one clearly. Okay, right. Beta mange car, scooter, baap, Raji. Next one, Bal Ganesh in Thailand. Boron, gallium, indium, thallium. Next, chemistry sir Geetam, having sneezing problem. Carbon, silicon, germanium, tin, and lead. Okay, so that's why stannous we call, and lead is plumbum we call, so that's why Pb. Next one, न्यूजीलैंड, पाकिस्तान, ऑस्ट्रेलिया सब बिक गया है। किसमें बिक गया? आईपीएल में बिक गया है। सो दैट इज नाइट्रोजन, फास्फोरस, आर्सेनिक, एंटीमोनी, बिस्मथ। एंटीमोनी मीन्स एसबी एंड बिस्मथ मीन्स बीआई। नेक्स्ट ग्रुप 70, हाँ ग्रुप 16। ग्रुप 16 इज हो साइंस से तेरे को प्रॉब्लम है। ऑक्सीजन, सल्फर, सेल्यूरियम, टेलूरियम एंड पोलोनियम। Okay, so this is the short tricks for the elements. Okay, so next last one is what? Fluorine, chlorine, bromine, iodine, cadmium. So that is father collector, brother inspector. And I told you to remember these elements also: boron, silicon, these metals also. ओ तेरे गीत सबसे भासी और आसान. So that is, these elements are the metalloids. Whatever the orange color we have given, those all are metalloids. Okay, you can easily remember. Okay, and next we discussed about the magic number trick. What we discussed about? We discussed about what? Magic number trick. So what is the magic number trick I told to you all? Can anybody tell me in the chat box? Magic number trick: 2, 8, 8, 18, 18, 32, and last is 32 plus. We don't know seventh period. So this is first period, second, third, fourth, fifth, sixth, and seventh period. Okay. So these are the periods, and these are the elements in each period. So the elements in the first period is 2, second period is 8, third period is 8, fourth period is 18. So these are very, very most important. So these are very, very most important. So any number you can easily find. Okay, let's suppose if I want to find the bismuth atomic number, I want to find the bismuth atomic number. So how do you find the atomic number of bismuth? Very pretty easily. How we can find it out? First, for nitrogen, you know the nitrogen atomic number is what? Tell me in the chat box. 7. So 7. It is belongs to which period? Second period. So then you need to add 8. Then this will become what? Phosphorus, you will get 15. Then again, you need to add 8. Okay, not 8. First for 2 helium is there, right? So for here you are adding 8. So next you add 18. So for 15, if you add 18, how much? 33. So arsenic, you are getting 33. Again, you add 18. So for 33, if you add 18, you are going to get what? 8 plus 3, 11. Okay, so that means 3 plus 5, 51. So arsenic, nitrogen, phosphorus, arsenic, antimony means this one, Sb. Okay, so that is how much? 51. So if this is 51 and this is 31 and this is 15 and this is 7 and 8, 18, 18. Next one is what? Next one is 32. So add 32 for 51, 383. So next you are getting bismuth. So bismuth atomic number is 83. So if you remember the magic trick number 288, 18, 18 and 32, you can find the atomic number. You can find the group period which it belongs to. You can also find the outer electronic configuration also very easily. So for 83, how do you write the electronic configuration? Now if you want to write. Good evening, Vardha team. Thank you so much. So for 18, if you want to find for the 83, if you want to write the electronic configuration, how do you write the outermost electronic configuration for 18? Just a minute, guys. Here power cut was there, so that's why I was having bit worry. Audio not clear, huh? Guys, am I audible or not? Please tell me in the chat. Am I audible or not? Please tell me in the chat box. My sound was very high. Come on, tell me in the chat box. Even my am I clear or not? Yeah, thank you. Thank you so much. Right, it's clear. Yeah, I'm turning off my video. The reason because here power cut was there. You guys can unable to see me, and simultaneously there is a issue here. Okay, so that's why I couldn't turn on. So please bear for me. Okay. Next 83. How do you write the electronic configuration of 83? Moeller diagram. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4D, 4F, 5S, 5P, 5D, 5F. So now 6S, 6P, 6D, 6F. Now remember, here we can fill 2, then here we can fill 2, then here we can fill 6. Yeah, thank you. Good evening, Rajkot team. Thank you so much. Okay. And 1s2, 2s2, 2p6, 3s2, then 3p6, then 4s2, 3d10, 4p6, then 5s2, then again 4d10, 5p6, 6s2. Just count here 2, 2, 10, 12, 18, 20, 30, 38, 48, 54, and this one 56, and then 56 plus 14, 56 plus 14, that is 10, 70, 70 plus 10, 80, and 83. So this is till here, that is the electronic configuration of bismuth. So like this also you can find the electronic configuration of any element. Okay, so I hope you guys can understand, and based upon that also you can write the by general electronic configuration. Okay, you can also write that one. Okay, so I hope everyone understand this one. So xenon. Okay, so xenon is this is 10, 18, 36, 54. So 54 till 54 it was there, right? So that is 4F14. Okay, 4F14, and again 5D10, 6P3. So this is the general electronic configuration of what? Bismuth. So for bismuth, this is the general electronic configuration. I hope everybody can remember this one very easily. Okay. Next. Yeah, so we have learned all these things. Tricks, just now we have found the tricks. What are the IUPAC names? We just found the tricks. So these are the recall test. What we have discussed in the previous class, these are the recall test things. Okay, na? So again, very, very most important, guys. Recall test is also really important for you all. So try to give the abbreviation for 119 and 109 and 114. I'll find for 119 and you can give it for other elements. So what are the 119 here? 119s are simply nothing but U, U, E. Okay. For 9, it is E, inilinium, inium. For 0, it is nil. Okay. So that's why U, U, E. And again, 109, U, N, E. Okay. 0 is for nil. So that's why U, N, E. Next, 114, U, U, Q. Why U, U, Q? So this is quadmium, quadra is come, so that's why we will got Q. Inium, nil linium, quadnium. Okay, so I told you to add just IUM at the end. You can easily find. Next, try to find for Z is equal to 112. Very easy, right? For Z is equal to 112, as we found for the bismuth, like that also you can easily find. Okay, for Z is equal to 112, we can easily find. So after finding that, you'll get an electronic configuration, okay, of how much? Z is equal to 112. That is radon, which is 86. I don't want to waste much time, so that's why I'm writing here. 6D10, 5F14, 7S2. Okay, so this is the electronic configuration from Euler diagram. Okay, they are asking about what? What is the which period it is belongs to? It belongs to seventh period, because highest principal quantum number will give the period. So that is seventh period. Group they are asking. So which group they are belong to? Again, you need to see the valence shell. So it is 7s2. So that is belongs to group 2. Okay. Next one, electronic configuration. We just have written the electronic configuration. And which block it is belongs to? It is belongs to seventh block. Okay, it is belongs to seventh block. Right. And it is 6D10, 5F. Okay, 7s2, right? Yeah, so very, very most important. Yeah, here D10 is there. So 6D is there, that is N minus 1 D is there, and NS is there. So that is 7S, and 7 minus 1 means what? 6 B is there. So that is why this is 10 plus how many electrons are there valency? 2. So this is 12 electrons are present. So that's why the group number is 12. So the group number is 12. Group number is 12. That is the answer for that one. Okay. Group number is 12. Okay. I hope you guys are clear with what I'm saying. Okay. And going to the today's topic. So if we are going to the today's topic is pretty clear, right? We have studied about S block elements. Just I am recalling the general electronic configuration of alkali metal is NS1 and it can easily lose one electron. So ideally they are having low ionization potential. These are alkaline earth metals NS2. They can easily lose 2 electrons. Very, very most important. These will have low ionization potential and that's why they can easily lose the electrons. They are metals. Usually they all are metals. Okay, and usually their reactivity is higher. Their reactivity is higher. Why the reactivity is higher? Because they can easily lose the electron. They can easily lose the electron. So that's why their reactivity is higher. Okay. And usually cesium and francium, barium and radium, they are radioactive elements. They are radioactive elements. Cesium and everything and all, they are radioactive elements. Okay. So this is another important point. आप सभी लोगों को याद होना चाहिए. Right. Next one, S block elements, the metallic character increases down the group, reactivity increases, except these lithium and beryllium. Lithium and beryllium, they usually form covalent bonds. They usually form covalent bonds. Yes, they also form ionic, but they are more favorable to covalent bonds because of small positive charge. Because of small positive charge. Small positive charge. So you will get to know about them in your chemical bonding very clearly by studying the covalent character from Fezan's rule. So you will understand this lithium and beryllium very easily from the Fezan's rule. Next, okay, P block elements. P block elements, we know the trick how to remember them. How to remember the P block elements. There are pnictogens, chalcogens, halogens. Pnictogens are very pungent or choking smell. These all are oxides and sulfides are formed. So that's why we call them as chalcogens. And fluorine, chlorine, bromine, iodine. These all are halogens means they can form sea salts or metallic salts. Okay. And the general electronic configuration is NS2, NP126. Okay. So based upon the particular group and whatever the orange color is indicated, these all are metalloids. What are metalloids? They are having a property both metals and non-metals. Okay. And another important thing I forgot to tell you, usually all metals are forming basic oxides. Basic oxides are hydroxides. Basic oxides are hydroxides except one metal, that is CrO3. Okay, Cr is a chromium is a metal, but still it is an acidic in nature. Okay, so these forms acidic oxide. So chromium oxide is basically an acidic oxide. I hope you guys are understand this one. Okay, P block elements, if you see down the group, again metallic character increases from left to right, non-metallic character increases. In middle they are metalloids. Okay, and the metalloids like BeO, Al2O3, Ga2O3, okay, SnO2, PbO2, okay, SbO2, Sb2O3, Pb2O3. These all are called as amphoteric oxides. Very, very most important. Very, very most important. ZnO is also amphoteric oxides. What is the meaning of amphoteric oxides? They can act as acidic oxide and basic oxides. Okay, they can act as a acidic oxide and basic oxide. If you see zinc, zinc can form, this is acidic oxide, right? Zinc oxide is an acidic oxide. Simultaneously, zinc hydroxide, it is also basic oxide. So the metals which are forming are the elements which are exist in both acidic and basic form are called them as amphoteric oxides. Or call them as what? Amphoteric oxides or amphoteric compounds or amphoteric elements. So amphoteric means they can act as both acidic and basic in nature. So simultaneously, these are the elements which usually form acidic and basic compounds. Again, stannous also form, lead also form, what we are going to, tin is also going to form. So these are very, very most important for your examination. Gallium, aluminium, zinc, okay, Fe2O3 and FeOH twice. So these are also amphoteric in nature. Very, very most important. Amphoteric means which are exist as both acidic and basic. I told you already. Usually they will form covalent compounds and their ionization potential is very high. But for the metals like 1A and 2A, their ionization potential is very low. Yes, guys, I'm going a bit faster, but you need to understand the importance of it. Okay. Next one is reducing character. Down the group, they can easily release the electrons. So that's why the reducing character increases. Okay. So if I'm going to ask you about any particular reducing nature, okay, NH3, PH3, okay, ASH3, and SBH3, like that, if I'm asking, the reducing character down the group increases. Okay, just remember, down the group, reducing character increases because they can readily lose the electrons. I hope you guys understand. Okay. Yeah. So, and usually they will have higher electron affinity, and these are most electronegative in nature. We will study about them separately. And I told you yesterday, D block elements, they do not show most properties. Very, very most important about their electronic configuration is N-1D, 10 NS2. Okay. I hope there is an internet interruption is there, guys. So bear me for 10 seconds. I will turn on the Wi-Fi hotspot because here net was not there. I can't help you. Yeah. Right. So I'm so sorry for the interruption caused. You can understand, there is a huge rain here in Bangalore. We'll see, we'll wait. If power will come, I will be available. If not, we can have it in the later classes too. Nothing much to worry. Okay. Alkali metals are, and they are usually colored in nature. They are having high melting point and boiling point. High melting point and boiling point, all the D block elements. And D block elements are called as transition elements because they always undergoing transition. Means for any reaction, the D electrons will always undergo in the transition. Okay, so that's why we call them as transition elements. And these transition elements has been designed with a particular property. What is the meaning of a transition element? Means they don't have unpaired electrons. Sorry, they need to be completely filled electrons that in d orbital. So how do you define a transition element? Means that should be completely filled d electrons, completely filled d electrons, or sorry, incompletely filled d electrons are called as transition elements. So zinc is also d block element, but not a transition element. Why? Because the d is completely filled. Simultaneously, cadmium is also d10, mercury is also d10, either in the common oxidation state or in the ground state. You may have wondered that sir, copper is also having d10, 4s1, 3d10, but still we are calling it as transition element. But copper exists in +2 oxidation state. So that is why 3d9 it came getting. So we can clearly say from here, which is having unpaired d electrons or not fully d electrons in those orbitals are called as transition elements. They exhibit color, just now I told, and they are paramagnetic in nature. Paramagnetic means they are having a magnetic property. Diamagnetic means no unpaired electrons is there. So due to they will have more unpaired electrons, so that's why we will having. And they will show variable valency. Variable valency means if you take manganese, manganese is existing +2, +3, +4, +5, +6, and +7. Okay. So it can exist in variable oxidation state, and they are usually colored compounds, and they can act as a catalyst in every reaction. If you see any organic reaction, they always act as a catalyst, promoters. And osmium, very, very most important, osmium Osmium is the element which shows highest oxidation state, that is +8. Okay, osmium is having +8 oxidation state. Guys, these all are the very important points. Okay, you just remember those things, or you just need to, just follow those things. And tungsten is having highest melting point, that is 2500 degrees Celsius. Tungsten is having what? Highest melting point, that is 2500 degrees Celsius. Osmium is having highest oxidation state. It can undergo +8. Okay, and another most important thing is copper, silver, gold. These are called as noble metals. These are called as noble metals. Very, very most important. And based upon this, you people need to remember the things. Okay. Next one, F block elements. These are also, metals only. Their atomic number starts from 59 to 71. These are lanthanoids. Actinoids are 91 to 103. So lanthanoids are 59 to 71. Actinoids are 91 to 103. We call them as inner transition elements. What we are going to call them as inner transition elements. So these all are called as inner transition elements. Okay. So these all are called as what? Inner transition elements. Okay. So just a minute, guys. There is one small interruption. So that's why I was right. Poor net connection was there. So sorry for the interruption cost. Inner transition elements. So they are also having high melting and boiling point. Okay. They are usually radioactive elements. So elements after uranium is called as transuranium elements. So next, metals. Just now I told all the metals are generally having high melting point. From left to right, metallic nature decreases, non-metallic nature increases. So usually they exist in solid state only. Usually they exist in solid state. Okay. Usually they exist in the solid state, but some of the exceptions are there. Mercury, gallium is they exist in the liquid nature, and because they are having low melting points. Very, very most important. Gallium and cesium are also metals, but they are having low melting points. Simultaneously, non-metals we can see. Okay. So yeah, another important, metals are usually ductile and malleable. What is the meaning of ductile? Means you can deform them into any shapes. Meaning of ductile is you can deform them into any shapes. What is meaning by malleable? You can make them into thin sheets. You can make them into thin sheets. Very, very most important point. Okay. And Guys, can you see my screen? Please tell me in the chat box. Guys, can you see my screen? Please tell me in the chat box. Please do reply. My voice might be breaking. Hello? Anyone there? Hello? Guys, please do respond in the chat box. Jane, yes. Thank you. Thank you so much. Yeah. So basically, these metals are, okay, just a minute. I will just, yeah. So basically, non-metals are having high electron affinity. So sorry, power came, then now we don't have any issues now. Right. So sorry for the interruption, guys. Thanks for your patience. How is the class, guys? Are you able to understand what is happening inside the class? Are you able to understand? Please let me know through the chat box. Are you clear? Am I audible to you? Am I audible? Is my voice is clear to you all? Guys, come on, anyone, please do reply in the chat box. Yes, thank you. Thank you so much, guys. So these are the properties we are just discussing about. Okay. So some of the properties, they are neither ductile nor malleable, but they are usually very reactive. Okay. Next one. Yeah, thank you so much. Next one, I told you how to recognize the metalloids. Okay. So I told you how to recognize the metalloids also. So what are metalloids? Metalloids are simply, they are amphoteric in nature. They are amphoteric in nature, means they can react with both acids and bases. What are metalloids? Silicon, germanium, arsenic, antimony, and tellurium. These all are the metalloids. So germanium, antimony, listen, germanium, antimony, and these both are going to form amphoteric oxides. So these metals can act as both metals and non-metals, but whereas these metals also act as metals and non-metals, but these two only form amphoteric oxides. Some of them are also lead oxide, zinc oxide, lead oxide. Okay, and Sb2O3 is also amphoteric oxide. ZnO is also amphoteric oxide. Fe2O3 is also amphoteric oxide. Okay, Ga2O3 is also amphoteric oxide. Very, very most important. Another one is Al2O3 is amphoteric oxides. So amphoteric oxides are very important for your examination. Okay, now this is another question. We can easily do this one. I don't want to waste my time much on this. Next, my favorite. Okay, so that is effective nuclear charge. What is the meaning of a effective nuclear charge? We are having 20 minutes. I'll cover all the basics of effective nuclear charge. Just focus here. So first of all, this is my atom, and we can clearly say from here. Let me take another color so that it will be very easy to understand. So this is my nucleus. Everyone will accept it. This is the nucleus. And what nucleus consists of? Neutrons plus protons. Usually we take it as positive charge. And we are having some inner electrons here. And this is the outer electron. So this is what? Outer electron. This is outer electron. And these are what? Inner electrons. Inner electrons. Carefully listen, guys. Very most important thing. Okay. Very most important. Careful. Just carefully listen. What is happening? Now tell me, electrons are having which charge? Negative charge. So all the electrons are having negative charge. So we know one thing. There is a positive charge and negative charge. There is a force of attraction between the nucleus and the electron. So between the nucleus and the electron, there is a force of attraction is there. Simultaneously between this electron and this electron, what you are going to happen? So between electron and electron, there is a repulsion is taking place. We call it as repulsive forces. Okay, so the combination of both force of attraction and the repulsion is given as Z effective, which we are going to call it as effective nuclear charge. What is the meaning of effective nuclear charge? The combination of both force of attraction between the nucleus and the outer electron, plus that is force of attraction between the nucleus and the outer electron, plus force of repulsion between the inner electron plus outer electron. I hope you guys understand. The combination of both is given as Z effective. So this is simply called as effective nuclear charge. Sir, how this effective nuclear charge depends upon? Very simple. By effective nuclear charge is depending upon Z minus sigma. Sir, what is this sigma here? What is Z here? Z is simply nothing but atomic number. Okay, Z is simply nothing but atomic number. What is the significance of atomic number? It is help us to find the number of protons. It is help us to find the number of protons. Simultaneously, if I'm talking about the number of protons, number of neutrons also will be there. So indirectly, Z will give the significance of the negative positive charge of the nucleus. Okay. And what is the meaning of sigma? What is the meaning of sigma, guys? What is the meaning of sigma? Sigma, for the first time, I think you are seeing. Sigma is called as screening constant. What is the meaning of sigma? Sigma is called as screening constant. What is that? Screening constant. Sir, what is the meaning of screening constant? Screening constant is calculated due to the presence of inner electrons. Due to the presence of inner electrons. Due to the presence of inner electrons, we are going to calculate the screening constant. I hope again I am repeating. What is effective nuclear charge? It is the combination force of between the force of attraction between nucleus and outer electron and the force of repulsion between the inner electrons and the outer electrons is simply nothing but effective nuclear charge. In sometimes in your NCERT, they will say nuclear charge. They simply say nuclear charge. What is the meaning of nuclear charge? Is considering only the force of attraction between the nucleus and the outer electron. So the force of attraction between the nucleus and the outer electron is called as nuclear charge. But what is effective nuclear charge? Effective nuclear charge is simply nothing but force of attraction between the nucleus and outer electron and the repulsive forces between the inner electrons and the outer electrons. Very simple. If the repulsive forces are dominant, Z effective decreases. If the repulsion forces increases, Z effective decreases. That's it. Why? Inner electrons will act as a shield. Inner electrons will act as a shield. I hope you guys clear with the effective nuclear charge. So Z effective is simply nothing but effective nuclear charge, which is the force of attraction between nucleus plus outer electron. Simultaneously, repulsive forces between outer electron and the inner electron. Okay, so this is the effective nuclear charge. So this depends upon Z minus sigma. Z is the positive charge indication and sigma negative charge indication, which we are going to call it as screening constant. And this is simply nothing but atomic number. Atomic number. I hope you guys understand what is the significance of this one. Okay. Now next we are talking about screening effect. What is the meaning of a screening effect? What is the meaning of screening effect? Again, everyone listen carefully. So these all are the outer electrons. So this is outer electron and these all are inner electrons. Let's suppose these all are the inner electron. N is equal to 1 and N is equal to, let's suppose, 5. Between there are some radius is also there. Just I'm ignoring them. What is happening here? The screening effect is simply nothing but due to the presence of inner electrons. Okay, what is going to happen? They act as screen or shield between the nucleus and outer electron. Very most important. What is the screening effect? Due to the presence of inner electron, they will act as a barrier or screen or shield between the nucleus and outer electrons. Because of the screening and shielding, we call this effect as called as screening effect. We call it as what? Screening effect or shielding effect. Very simple in our layman language. If I say in layman language, if I am saying, what is that one? That is due to the presence of the inner electrons. ये सारे क्या है? The red wala, these are the inner electrons. Due to the presence of inner electrons, what is going to happen? They are acting as a shielders. They are acting as a shielders. So that's why they will decrease the Z effective. They will decrease the Z effective. More will be the screening, less will be the Z effective. We can clearly say that Z effective is inversely proportional to the screening effect. Z effective is inversely proportional to the screening effect. Okay, so as the Z effective increases, the screening effect decreases. Or if you are increasing the screening effect, all the inner electrons will going to block. All the inner electrons will going to shield the outer electrons, which decreases the effective nuclear charge. Now tell me, what will going to happen for this electron? Yes, if the screening effect is increases, outer electron can remove easily. Outer electron can remove easily. That's why you are having low ionization enthalpy. Sir, what you are talking about low ionization enthalpy? We'll talk about that one later. Just focus here. So if the screening effect is increases, the outer electron can easily remove. So screening effect is simply nothing but they will block or they will shield the attraction between the nucleus and the outer electron. Now, which electrons are more shielders? Very simple. S electrons are more shielder than P, than D, than F. Usually D and F are called as poor shielders. Usually D and F are poor shielders. S and P are very strong shielders. Okay, usually S is very strong shielders. Why? Because they are near to the nucleus. They are near to the nucleus and they are spherical in shape, or we can say the boundary surface plots. The boundary surface plot of S and P are very near to the nucleus and they are very easily block the outer electrons and they will reduce the force of attraction between the nucleus and the outer electron. I hope you guys understand this one. Okay, I hope it is clear to you all. Next, screening effect का हो गया था. So remember, screening effect is inversely proportional to Z effective and it is directly proportional to the reactivity. If the screening effect is increases, reactivity of the metals is increases, and we can also say S can screen more than P, then D, and then F. Okay, I hope you guys can understand this one very clearly. Now, next one is diagonal relationship. What is the meaning of diagonal relationship? Usually, diagonal second and third period elements are there. No, second and third period elements are there. Usually, second and third period elements are there, like lithium, beryllium, Okay, boron. Okay, so these are all the second period elements: lithium, beryllium, boron, next carbon. So these are second period. What about third period elements? Sodium, magnesium, aluminum, and silicon. Okay. Thank you, Sangli team. Thank you so much. So usually, yeah. So now usually there is a similarities between the second and third period. There is a similarities between the second and third period. So where the similarity is taking place between the lithium and magnesium, beryllium and aluminum, boron and silicon. In what way of similarities are there? There are some properties. There are some properties. We know atomic size. What will going to happen for atomic size? From left to right. Okay, from left to right, size will going to decreases. From top to bottom, size increases. Because as the Z effective increases, or we can say due to the addition of new cell, due to the addition of new cell, the size will increase. This is the reasons for that. Now, but diagonally, if you are going diagonally, there is one chance here. There is one chance here. That is what? That is, we can say that, just a minute, guys. Yeah. So due to the diagonal relationship, the atomic size of lithium and magnesium are nearly same. Those are, this is 1.23 angstroms and magnesium is 1.3 angstroms. So they are nearly same. Or if you take Li plus and Mg plus size, ionic size also, those are 0.76 and 0.79. So the atomic size is nearly same along the diagonal. So that is why these two will exhibit diagonal relationship. This is the first property. Second property, electronegativity values. If you see the electronegativity values, lithium and magnesium have a similar, very nearly electronegative values. This is having 1 and this is having 1.2. Okay, so 1 value and 1.2 values. These are the electronegative values. What are electronegativity? The tendency to pull the shared pair of electrons. So it is having 1 and it is having 1.2. So this is the one diagonal relationship. If you see for the beryllium and aluminum also 1.5 and 1.5. So they are having equal electronegativity values. That is why second period element of beryllium is having a diagonal relationship with third period element of aluminum. So this is what diagonal relationship. And third, charge by size ratio. Charge by size ratio, or we can say radius ratio. We can say that radius ratio. So charge by radius ratio of aluminum, beryllium and aluminum, lithium and magnesium is nearly same. So that is why, because of these three properties, elements of lithium and magnesium, beryllium and aluminum, boron and silicon are existing diagonally related. What are the three properties? Atomic size, electronegativity values, and charge by size ratio. That is why these elements are having a diagonal relationship. I hope you guys are clear with this. If you are clear, I'll move to next one. Please let me know through the chat box, guys. Tell me in the chat box. Guys, is it clear to you? Sangli or any team, please let me know through the chat box. Guys, come on. Yeah, thank you. So diagonal relation, we have finished it. Yeah. Next one is lanthanoid contraction. What is the meaning of lanthanoid contraction? I told you lanthanoids are there from 59 to 91. These all are what? Lanthanoids. They are exist at the fourth and fifth period. They are exist at the fourth, fifth, and sixth also. Sixth periods. And lanthanoids, and we can also say actinoids also. Actinoids is also there. Actinoids is also there. Okay, So these are the actinoids from 90 to 91 to 103. These are actinoids. So there is some contraction is taking place. Now, what are these? Let's suppose if I'm talking about any particular elements, if I'm talking about any particular elements, lanthanoid contraction we are talking, right? So what are the lanthanoid contraction we can see here is, just a minute, give me time for 1 second. We'll give you the exact meaning of lanthanoid contraction. Nothing to worry about here. Lanthanoids contraction. I want to give you perfect clarity. That's why. Yeah, okay, let it be. Very easy, right? That is, this is n is equal to 1, and this is n is equal to 2, n is equal to 3, and n is equal to 4. Let's suppose this is the outermost electron. Okay, so let's suppose n is equal to 5. So this is the valence electron. This is valence electron. So this is valence electron. Now let me take another color so that it will be very useful for you. Right. Now you can clearly say from here. Now you can clearly see. So for 1s orbital, you are having 1s only for n is equal to 1, 1s. For 2, 2s, 2p. For 3, 3s, 3p and 3d is there. But for 4, 4s, 4p, yes, 4d and 4f. Very good. So now due to the presence of, due to the presence of 4f and 4d electrons, due to the presence of 4f and 4d electrons, if you see the nucleus, so in the nucleus, all the s electrons are very good shielders. We know all the s electrons are very good shielders. P, yes, they can also shield, but the major problem with the d electrons is they are widely spread. They are widely spread. Even for s electrons also, these are d electrons and these are f electrons. Then due to the poor shielding of d and f electrons, due to the poor shielding of d and f electrons, the z effective over outer electron increases. Why? You can clearly see from here. You can clearly see from here. These all are the d electrons. So I'm indicating with black color. So these all are the d electrons and these are the f electrons. Okay, there is a very gap between them. So now due to the gap, the effective nuclear charge increases. So let's suppose these are s electrons, these are d electrons and these are f electrons. Okay, these are d electrons and these are f electrons. This is outer shell. So due to the poor shielding of d and f electrons, the effective nuclear charge over outer electron increases, z effective increases. So the electron will slightly pulled inside. Due to the slightly pulling of the electron, the size of the atom will decreases. Because of this contraction or because of this decrease in atomic size due to the presence of d and f electrons is called as lanthanoid contraction. I hope everyone understand what is the meaning of a lanthanoid contraction. Due to the presence of d and f electrons, there is a decrease or there is a contraction of the atomic size of outer electron. So that is why there is a decrease in the size. You can see there is a decrease in the size of atom due to the inward pulling of z effective. ये outer electron क्या हो जाएगा, अंदर pull हो जाएगा, इसीलिए उसका lanthanoid contraction हो जाएंगे. I hope you guys understand about this one. Is it clear to you all? So again, I will finally summarize. Lanthanoid contraction is happening because of the poor shielding of d. These are d electrons and these are f electrons. So this is the valence shell. These are d electrons and these are f electrons. Usually these all are poor shielders. Due to the poor shielders, what will going to happen? Z effective over outer electron increases. Due to that, the electron will slightly pulled inside. So the new atomic radius, or we can say the new atomic size has been contracted. So there is a contraction is taking place. So this contraction is due to poor shielding of d and f electrons. Is called as lanthanoid contraction. I hope everyone is clear with this. I hope everyone is clear with this. Clear? Yeah. So last concept, inert pair effect. Inert pair effect is very simple. That is usually observed at gallium, indium, and thallium. In these elements only we will see the inert pair effect. So what is inert pair effect means? So these elements, even in germanium, antimony, and lead. So among these, arsenic, bismuth, and antimony. So among these 9 elements, you will observe the inert pair effect. What is inert pair effect means? Usually they should exist in +3 oxidation state, but gallium is very stable in +1 oxidation state. So I will explain this one in the next class. I think it takes some 5 to 10 minutes of time. So I don't want to waste much time of yours as it is Sunday. You guys take some relax, have fun, try to revise this concept and try to study very hard. What is the Z effective? What is screening effect? And what is lanthanoid contraction? What is the diagonal relationship? All these things are. Shall I go ahead? Shall I go ahead? Or shall I stop here? Yeah, thank you. Thank you guys. I am very interested to teach. There is nothing wrong. So just listen here very carefully. People who want to leave, you can leave. Others, please stay here. Okay. So now inert pair effect, very, very most important. What is inert pair effect is? Okay. We know, especially if you take these elements, usually which is consists of Ns and N-1d electronic configuration. Where you will observe this configuration? This configuration usually we observe in these elements. In these elements only you will observe. In gallium, indium, thallium, tin, lead, bismuth. Okay, here only we'll observe. Just before we have, let's suppose if I'm talking about lead. So if I'm talking about lead, what is the atomic number of lead? What is the atomic number of lead? How do you determine the atomic number of lead? Chemistry, sir, gay, sneezing, problem. Let's suppose. So we can say this is 4, this is 14, again add 18. So this will become 32 and 32 ko 18 add kar do. 32, if you add 18 means 50, right? Yeah, 50. And again, if you add 32, so this is 82. So now 82, if you see the 82, you can write it as what? Xenon. Last time we have written 5F 14, 6D 10, 7S 1, I think. Just a minute. Let me check the xenon electronic configuration. 82, right? Just a minute. Generally for this one is what? NS2, NP2 is the outer electronic configuration. So sorry guys, let me erase everything to give you the clarity. No need to worry about this. Now we are writing the electronic configuration of lead. So lead belongs to which family? Carbon family. Lead belongs to which family? Carbon family. So how do you remember? Chemistry, sir, Geetam, having which problem? Sneezing problem. So this is NS2, NP2 is the general electronic configuration. That is, this will become 2S2, 2P2, 3S2, 3P2, 4S2, 4P2, and here 5S2, 5P2, 6S2, 6P2. So the outer electronic configuration is 6S2, 6P2, and simultaneously before that, there is a electronic configuration of this one. Okay, so this is 83, right? So 83 for this one, if you are writing for 83 for the, sorry, 82. So if you write for the 82, how I are going to write? 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 5S, 5P, 5D, 5F, 6S, 6P, 6D, and 6F. Now 2, 2, and 6, 2, 6, 2, 10, 6, 2, 10, 6, and 2, and next here 10 and 2. So now if you see the general electronic configuration, so here it is at 54. Xenon is 54, right? Xenon is 54 up to where it is coming? 10, and 12, 18, 20, 30, 38, and 38, 48. This one 654. So till here, this is 54. And next 6s2, 5d10, and 6p2. Now you can see there is an involvement of d electrons here. Now remember very clearly, if you are writing like this, so these all are what? N is equal to 1, 2, 3, 4. This is 4, and this is 5, and this is 6. So here 2 electrons are there. These are s electrons. Okay, and these all are p electrons. These are our p electrons. Now what will going to happen? Due to the poor shielding of 5d electrons. Okay, due to I'm writing here again. So 1, 2, 3, 4, 5, 6. So here this we are having what? These all are 5d electrons. These all are 5d electrons, and this is 6s2 electrons, and these all are okay. These are 6s2 electrons, and these are 6p2 electrons. So due to poor shielding of 5d electrons, what is going to happen? The effective nuclear charge over s electron will increases. The Z effective over 6s2 electrons increases. So 6s2 electrons penetrate inside the nucleus. Means towards, not inside, towards the nucleus. So क्या हो रहा है? Simple, अपना normal language में बात करें. So what will going to happen? Due to the poor shielding of d electrons or f electrons, what is going to happen? The outer 6s electrons are slightly shifted towards the nucleus. When they are slightly shifted towards the nucleus, these 6s2 electrons are reluctant to participate in the reaction. सिंपल सी बात ये कहना चाहता हूं, आप लोग 4 दोस्त हैं, उसमें 2 P सेक्शन के लोग हैं, 2 S सेक्शन के लोग. There are 4 friends. In those 4 friends, one belongs to Sangli and another belongs to Pondicherry. Let's suppose JNV Sangli team, 6s2 are JNV Sangli and 6p2 are JNV Pondicherry. So what happened? Due to less shielding, due to the poor shielding of 5d electrons, all 2 JNV Sangli students are moving towards the nucleus. Two electrons are moving towards the nucleus. So when they are moving towards the nucleus, they are unable to come out of it. So lead can only exhibit +2, cannot exhibit +4. Okay, lead can exhibit only +2, cannot exhibit +4. Simultaneously, if you look for gallium also, gallium exhibit +3, but the most stable state is gallium is in +1 only. Simultaneously, indium can exhibit +3, but the most stable state is +1. Okay, simultaneously thallium can exhibit +3, but it is most stable state is +1. Why? Because of inert pair effect. Because of inert pair effect, all these elements will stable in the +1 oxidation state. Okay, now let me, so I will erase this one so that it is understanding to you all. Very simple. Inert pair effect is observed in boron, carbon, and nitrogen family. Where N is greater than or equal to 4. We are going to observe in boron family. कहाँ observe करेंगे हम? Germanium, okay, gallium, indium, and thallium. They will exhibit only +1 state, but +3 state is not stable. Why? Because of inert pair effect. Okay, And next, in carbon family, if you see in the carbon family, what is going to happen? Carbon family, who are the elements are there? Tin, lead, germanium, tin, lead. They has to exhibit plus 4 oxidation state. They have to exhibit plus 4 oxidation state because the outer electronic configuration is Ns to Np2, but they will not exhibit plus 4 oxidation state. They are stable in plus 2 oxidation state. Because they are not stable in plus 4, same inert pair effect. Inert pair effect. Simultaneously, from nitrogen family, what is that? Arsenic, antimony, bismuth. Okay, arsenic, antimony, and bismuth. So these are also should exhibit in which state? Plus 5, plus 5, plus 5. But they will not exhibit plus 5. They will exhibit only plus 3 state. They will exhibit only plus 3 state. Why they will exhibit plus 3? Why not plus 5? Same inert pair effect. So inert pair effect के वजह से heavier elements जो होगा वो smaller oxidation states are highly stable. Very important. Plus 1 is more stable than plus 3 in case of boron, and in case of carbon family, plus 2 is more stable than plus 4. In case of nitrogen family, plus 3 state is more stable than plus 5. Very, very most important. Okay. So why I am telling all the things? Because why I am telling all the things? Because just remember very clearly. Just remember very clearly. In your examination, they will ask which of the following element compounds are possible. Compounds are possible. Let me give the examples. Okay, I'm giving you Bi I5, Bi Cl5, B Pb F2. Okay, next one is TLF3. Okay, and TL2O3. Okay, now if you write this one, Bi plus 5 and 5i minus. I told Bi plus 5 is not stable, so this is not going to exist because Bi plus 5 is unstable compared with Bi plus 3. Okay, and BiCl5 is also not exist, but lead Pb is existing plus 2, it is possible, and tellurium is existing plus 1 plus 3 F minus, so this is also stable, and TL2O3 means that is TL plus 1 plus 2 TL plus 1 plus 3 O2 minus, so this is also exist. So these 3 elements exist, these 2 will not exist. Very simple thing आपका माइंड में ये होना चाहिए कि जब भी आपको हेवी एलिमेंट्स देता है, बिस्मथ, लेड, टिन, जर्मेनियम और ऐसा मतलब टिन, थैलियम, इंडियम, अगर इस तरह का एलिमेंट्स देते हैं उसका स्मॉलर ऑक्सीडेशन स्टेट होगा ना, स्मॉलर ऑक्सीडेशन स्टेट, they are stable. That's it. I hope you guys understand this one. Please let me know through the chat box. I think last concept bit complicate किया, next class में और अच्छे से समझा दूंगा उसका, ठीक है? Don't need to worry about this. I hope you guys all are understand this one. Please let me know through the chat box. 10 minutes extend हो गया guys, so sorry. Guys, shall I leave? How is the class today? Please comment. How is the class today? Please comment. JNV Sangli team, how is the class today? Thank you so much. We'll meet you on next week. Okay, that is Tuesday we are going to meet again. Okay guys, thank you. Okay, yeah, thank you Mahe team, right? Thank you so much guys. I'll see you in the next class. Bye bye.